Hi, my name is Brett Throkel. I'm the Application Manager at Advanced Illumination. I wanted to welcome you to my series, Mastering Machine Vision Inspection, and take a few minutes to talk about one of the four cornerstones of machine vision illumination. The four cornerstones concept was devised as a teaching tool for labeling and demonstrating four methods that can be applied to enhance or create appropriate image contrast of parts versus their backgrounds. The four cornerstones consist of geometry, pattern and structure, filtering, and wavelength. As one of the cornerstones, filters play a crucial role in machine vision by enhancing image quality, extracting relevant features, and reducing noise, leading to more accurate, efficient, and reliable performance. The ultimate goal in understanding the four cornerstones is to have effective, consistent, and robust features best suited for a given inspection. A frequently asked question concerning the four cornerstones concept is priority of investigation. For example, is wavelength more important than geometry? Should we first be starting with structure? And when do we apply filtering? There's really not an easy answer to that question. The steps you take will depend on the part and the expected application-specific results. The geometry and structure are more important when dealing with specular surfaces, whereas wavelength and filtering are more crucial for color and transparency applications. Understanding how manipulating and enhancing the image contrast from a part against its immediate background using the four cornerstones is crucial for assessing the quality and robustness of the lighting system. Of course, it's not uncommon to find that more than one cornerstone is required to solve an application. Using filters in machine vision offers several crucial benefits, making it a vital tool for various applications. Filtering can help to enhance contrast, reduce glare, or can be used to transmit or block specific wavelengths, including visible and non-visible. They can help to improve the efficiency of the processing times of your machine vision systems. One rule to always remember in machine vision lighting: contrast is king. Filters can selectively block or emphasize specific wavelengths of light, highlighting the features of interest while suppressing irrelevant background information. This improved contrast makes object detection and recognition more accurate and efficient. Polarizers can block unwanted reflections or ambient lighting, minimizing noise and glare that can interfere with image analysis. This allows for more accurate feature measurement and object classification. The human eye is able to see the visible spectrum from roughly 400 to 700 nanometers, whereas a typical camera sensor is capable of seeing a range from the upper ultraviolet to near infrared wavelengths. Some filters pass specific wavelengths not visible to the human eye, like near infrared or ultraviolet, providing additional information for analysis. This can be invaluable for tasks like material identification or flaw detection, which may be invisible in regular light. By filtering out irrelevant information, filters reduce the amount of data the vision system needs to process. This makes image analysis faster and less computationally expensive, especially for real-time applications. For example, here we have a bolt with ultraviolet infused glue on the sealing surface. When imaged with a UV ring light, the highly speculative surfaces produces too much glare to fully detect all defects. On a production line, a bandpass filter can block the unwanted UV wavelengths and only pass the desired emitted wavelength, thus improving the image for the vision system. A wide variety of filter types allows for tailored solutions based on the specific needs of the application. This adaptability makes machine vision versatile and applicable to diverse scenarios. Bandpass filters transmit a specific range of wavelengths, ideal for highlighting features based on color. Long pass filters pass wavelengths longer than a cutoff point, useful for removing unwanted reflections. Short pass filters pass wavelengths shorter than a cutoff point, often used to block infrared light. Polarization filters can be used to reduce glare and reflections. So how does polarization work? Imagine light traveling from a light source to the target as uncontrolled sine waves, traveling in multiple planes as unpolarized light. A single piece of polarizing film is placed between the light and the target, which will absorb all of those sine waves that are not aligned with the film. This allows only one plane, in this case a vertical plane, to pass through. A second polarizer, called the analyzer, is placed over the camera lens. Rotating the analyzer allows the operator to isolate the polarized light in the direction perpendicular to the glare, reducing the glare perceived by the viewer. One thing to keep in mind is that a single polarizer will cut your light intensity by 50%, since only half of the amount of light is being passed along the transmission axis. Using the analyzer will reduce your intensity further as you reduce the glare. Another thing to understand is that the light which is being blocked by the polarizing film along the absorption axis is being absorbed by that film and creating a lot of heat. This heat limits the life cycle of the polarizing film. Polarized backlighting is best used to detect internal stressing or structural damage in transparent materials. Polarization in machine vision is also employed to primarily block specular glare reflections from surfaces that would otherwise preclude a successful feature identification and inspection. Since the light intensity will be reduced by 50% or more, you will have to increase your f-stop, which may reduce your line speeds and feeds. In some instances, fluorescing agents are used to highlight features of interest. When pairing a light source that matches the peak excitation of a fluorescing agent with a bandpass filter matching the emission wavelength, the viewer can isolate the fluorescing agent against its surroundings. In this example, we're imaging these nylon-impregnated hex nuts with UV light and strong fluorescent lighting. We can see that the nut on the left is missing its inner O-ring, but is it really robust enough for our vision system to pick up? Taking into account the wavelength for the light emitting from the ring, we can apply a blue bandpass filter, which blocks the UV excitation light as well as the ambient light. This leaves us with an effective, consistent, and robust image for the processing system. Another type of filter that we use is collimation film. With traditional machine vision backlighting, standard LED backlights emit light rays in various directions, creating a diffused illumination. This diffusion can cause the edges and details to be blurred due to scattered light. Additionally, different parts of the object receive varying light intensities. Collimation film acts as a filter, allowing only light rays within a specific angle to pass through. By restricting these angles, the light becomes more collimated for better contrast, meaning it travels close to parallel straight lines. This results in sharper edges and clearer details due to reduced light scattering and more consistent light distribution across the object. Benefits of using collimation film include improved image quality for sharper images with better contrast. This enables more accurate measurements and defect detection and reduced noise. Less stray light interference leads to cleaner images with less noise. It should be noted that not all backlighting applications require collimation. It's best to choose the approach that best suits your specific needs and object characteristics. One last thing to consider is the passage of electromagnetic radiation through a material. This property causes some materials to appear opaque to the human eye, while other materials pass infrared wavelengths, allowing vision cameras to see through what would otherwise be perceived as a non-transparent material. My father started AI in his garage over 30 years ago, and we were the first machine vision LED lighting company in existence. As such, we pride ourselves on being a full customer support company. If you need assistance with an ongoing or a future application, please don't hesitate to reach out to me. I would also encourage you to download our practical guide to machine vision lighting. This comprehensive handbook covers everything I talked about today and much more. If you're looking to get into the machine vision lighting industry or would like to refresh principles that you learned in the past, this industry-leading lighting guide is the best place to start. Thank you for your time today.